Welcome back to the channel. In today's video, we're going to continue looking at near-infrared data. And in the last video, we focused a lot on using a combination of signal processors like Sierpinski-Golay and standard normal variate to process the data. We then used correlation analysis to remove the bad replicates. And throughout that process, we visualized the changes using a combination of PCA and a scatter plot of that score's data. However, in all of that, we had a few unknown samples that we largely ignored in the last video. Those unknowns can be viewed here in orange, where 3 of those unknowns cluster near the polypropylene samples here, and 1 of those unknowns cluster near the polyester samples illustrated in the light blue there. Now, PCA cannot tell us the identity of those materials or help us predict the materials. However, we can leverage the benefits of PCA, the ability to compress the data, to simplify the data, and then feed that simplified data, that scores data, into a supervised machine learning model for prediction of these unknowns. And I want to show you the benefit that we can gain by using PCA, particularly when coupled with very wide analytical data. Let's get started. So the goal now is to see if we can predict these unknowns. And at first, we're going to just feed in the raw processed data. To do so, we're going to use a support vector classifier. We're then going to use train test split to determine how our model is performing on the labeled samples. And we're going to evaluate the metrics using F1 score and accuracy score. And the next step, we're going to instantiate our support vector classifier with a random state of 3. We're not going to do much to try to improve the model during the instantiation because I want to demonstrate the benefit of PCA. But of course, there are other attributes we can pass in here. We're going to create a mask so we can filter our unknown samples out. And then we're going to create 2 variables, X, where we have our filtered data. So this is all the analytical data without the unknowns. And then we're going to create an X unknown variable that we'll eventually use to predict with just the unknown samples. And then our Y, which will be just the labeled data. When we run this, we can start to get hints at some problems that might exist with our current design of this data. If you look at the shape, we have 90 samples and 212 variables. And so our data is very wide, and this can pose significant challenges for a machine learning model to predict the important variables. Now, these challenges can be circumvented in a number of ways, and in this, I'm just going to demonstrate the benefit of PCA. Secondly, we have, just to help clarify, if you look at the Y variable, we have 5 classes we're trying to predict: HDPE, polypropylene, polyethylene terephthalate, low-density polyethylene, and polyester. So next, we're going to use train test split to split the data into a training set and a test set, and we're going to hold back about 20% of our data for testing. We're going to actually fit the model at this line here, and then we're going to create our predicted labels from our training set and our test set using CLF predict, and then evaluate the performance of those models using the F1 score and accuracy scores for our training and testing data. When we pass in all of the data into the model, you can see that it doesn't perform very well. Our F1 scores are around the mid-40s, and our accuracy scores are in the mid-50s. And generally speaking, when you're talking score, you want values closer to 1 to suggest high performance. So next, let's see how our model performs in predicting the labels for our unknowns. To do that, we will just use the predict method and pass in X unknown. And in this case, it's predicting all of our unknown samples as high density polyethylene. And this could be because we have a lot of high density polyethylene samples, but visually it seems like we would expect at least 3 of them to be polypropylene and perhaps 1 to be a polyester sample. And so this isn't what we would expect and perhaps would give us some pause. But let's see how the model performs when we use PCA as part of our pipeline. So this is highly simplified. Generally, we would actually create a PCA model on just the training set and then use that on the test set. But I'm just going to use our original PCA and just focus on the supervised machine learning process. So to do that, let's create a new variable X. And that's just going to be the scores data, and we're going to pass in the same mask. And then we're going to also update our X unknown. And we're going to pass in, again, the scores data and our reversed mask. So this will just give us the unknown data, and Y will remain the same. When we do this, we can see that now if we look at X and just focus on the shape, it has the same 90 samples, but only 4 variables. And this data compression comes because of the benefit of PCA. We're going to keep everything else the same here because we were using all the same variable names. And we're going to now run this, and we can see that our F1 score and our accuracy scores for both the training and test sets are significantly improved, almost doubled over the full data. And this is likely because it's easier for the model to find the important patterns within this reduced data, this compressed data, than it could when we looked at the full NIR data. And importantly, let's see how this model now performs in predicting our unknowns. And in this case, we can see that it's predicting 3 unknowns as polypropylene and 1 as polyester. And this goes with what we were expecting based on the PCA data, that 3 of them do look like polypropylene and 1 is much closer to polyethylene. There's other ways that we might be able to get at this by regularizing the model, but this is just another benefit of PCA, not just for unsupervised learning or data visualization, but also improving the performance of some of your supervised models, particularly for analytical data. If you have any questions or want to see more like this, let me know in the comments, and I'll see you in the next one. Peace.